My connection with StatMech comes through plasma physics. So in my PhD at IIT Madras, I started studying how these charged particles behave in the presence of electromagnetic fields. And from electrical engineering, I moved to plasma physics, and now I'm seemingly moving more towards StatMech. And this work that I did was done in collaboration with Vered at Weizmann, Dimitri at Imperial, and Vasily at Warwick. So before we get into Fermi acceleration, we need to understand what this simple mathematical toy is called dynamical billiards means. So basically we have a simple geometry of some arbitrary shape, and we have a particle which is moving inside this geometry, undergoing elastic collisions with the boundaries. So in general, broadly speaking, these billiards can be divided into three kinds. One of them is integrable. As you can see, a rectangle or an ellipse is an example of an integrable billiard. These polygons, which is especially what I study, are pseudo-integrable billiards. We'll come to what this means. And this was shown by Michael Berry. It's the same guy who invented Berry phase, that he gave very nice formulas to sort of show why these polygons are pseudo-integrable billiards. And of course, we know about chaotic systems. So this was the first example of a chaotic system which was given by Sinai, which is just a rectangle with a small disk. And this is known as a stadium. This model was given by this guy Bunimovich. So what does pseudo-integrability mean? I think to understand my work, it's very important to understand what this concept means. So when we talk of integrable systems, the first definition was given by Arnold in the 1960s, and he said that if you have an n-dimensional system which has n constants of motion in involution, then that system is integrable. But in the 80s, Kozlov and Dwestermath independently showed that such systems need not have n global action angle variables. So you can have systems which have n-dimensional systems which have n constants of motion, but they need not have n global action angle variables. And these systems are what is known as the pseudo-integrable systems. And motion in these systems, instead of being given by a torus, is given by these collection of tori which are sort of joined together in the form of handles. And what in Fermi acceleration what we study is what happens to these billiards when we periodically oscillate the boundaries. So we have a particle inside this billiard. It is undergoing elastic collisions with the boundaries. So in the static case, there is no change of energy, only the direction of the particle changes. But when my ball is moving periodically, then depending on whether my ball is moving away from the particle or towards the particle can either lose or gain energy. And the question is, what happens asymptotically as time goes to infinity? Ball is moving independent of the particle with an infinite mass. So the ball does not undergo any changes in its velocity. So the hope is that, of course, we are interested in this question of what happens with the particle energy with infinite time, but the hope is that then we can perhaps go back and understand some more properties of these pseudo-integrable systems in some more detail, which are not so obvious when we study the static case. Okay, so this problem has been studied since in the 1940s. So in 1949, Enrico Fermi made a conjecture that these rectangular systems with an oscillating wall will lead to an unbounded growth of energy of the particle. That was his conjecture. But it kind of took around 34 years, and in 1983, a Russian called Pustelnikov actually gave a proof by using Km theorem that in this 1D system, this rectangle, the energy actually remains bounded. So he actually disproved Fermi's conjecture. Only this wall is moving periodically. Only one. You can also move all the walls, but that doesn't change anything actually. Okay. So in the case of an ellipse, although it is also an integrable system, but it is 2D, so you have a 4D phase space. So there you can have a slow Arnold diffusion, because of which you can have a very slow growth of energy, but it is so slow that you cannot really call it acceleration. Then later on in the 1990s, these chaotic systems were studied by people from Russia, and here they found that the acceleration is actually quadratic in time. So in 2010, when I went to Weizmann in Israel, there I started studying these pseudo-integral systems or these polygons, and what we found very interestingly is that they have exponential energy growth. And as far as I know, this is, I think, the first demonstration of exponential energy growth in a dynamical system. And here one may think that if a system is chaotic, it should be more random and lead to more energy growth. But actually what happens is that chaotic systems have very good averages. So because of these very good averages, the exponential growth rate also averages out to 0. So what you actually have is just a quadratic growth because of just noise correlations. But in a pseudo-integrable system, there are no such good averages, because of which the rate of exponential growth is actually positive. And we have mathematical models which are supported by numerical results to show all this. But what is still lacking in this field is there is no mathematical proof. So even for the quadratic growth in a chaotic system, there is no proof that the growth will be quadratic. We have mathematical models, and the results match very well with simulations. So now, although in these pseudo-integrable systems we have exponential growth, but one problem with these accelerators is that if you even slightly deform this geometry, then the exponential growth might go away, because in an experimental setting, if you want to realize this practically, you cannot actually have a absolutely flat line. There will be some deformation, and in that case, what happens is not very clear. So in 2011 in PRL, we showed another system which is a robust exponential accelerator, where it doesn't matter what your geometry is. But this is slightly different from Fermi acceleration, because here what we do is that you have this region, a connected region D, so you slowly deform it and then you pinch it off over here. So now you have separated this into two different subsystems. Then you again start joining it back, you form this, again a connected system, you again deform it and move it into two systems, again connect it back. So we showed again through a mathematical model based on random walks, and which were matched with experimental results, where the growth rate was exponential, and it didn't matter what the shape of this connected domain is. So this was a very robust kind of an exponential accelerator we have. So far it's very nice that everything matches very well. But in any real setting, for example, these systems are used for studying the heating of plasmas in RF fields. And there, one thing which is different from Fermi acceleration is that in a real plasma, the plasma doesn't remain confined within this accelerator zone. So there is exchange of particles from within the billiard to the outside domain. So, but these Fermi accelerators have particles confined within their domain. Particles don't come in or go out. So in order to model the exchange of particles, what we did is that we introduced a small hole in this Fermi accelerator. So we studied these Fermi accelerators next, where we introduced this small hole so that particles could come in and go out at a certain rate. So again, we studied two kinds of these accelerators. One is this exponential case, where there are also some general results which are shown by my collaborators that if you have a non-ergodic system, then in general it will have exponential acceleration, and if you have an ergodic accelerator, then in general it will have quadratic energy growth. So the question we are asking is, what is this energy gain? So this G as a function of E in is defined as this. So this H times V in sort of measures how many particles are coming into my system at a given time. That what is the rate of entry of particles into this system, and this E out minus E in is sort of the change of energy between the moment at which the particle exits my system compared to the time at which it enters the system. So in order to construct the mathematical model, we made two assumptions. One assumption is that the hole size is very small and does not affect the billiard statistics. So the assumption is that even if I introduce this small hole over here, my particle still undergoes this exponential acceleration for that amount of time before it exits the billiard. And the second assumption was that the average number of collisions before exit, this average of n, depends linearly on 1 by h, where h is the hole size, and it does not depend on the incoming energy. So these were the two assumptions, but we have also verified numerically that these assumptions are indeed correct. And under these assumptions, we have been able to do some calculations based on our earlier work also, where we find that in the quadratic case or in the ergodic case, the average energy gain depends on the input energy linearly, on the input velocity linearly. But in the exponential case or the non-ergodic case, it depends also on this hole size. So this is the most crucial point of this work, that if you have an ergodic accelerator, then the net energy gain is independent of your hole size, as long as your hole is small enough. Okay? But in the exponential case, you can actually increase your hole size, you can actually increase your energy gain by decreasing the hole size. So that is actually a very counterintuitive kind of a thing, that you would think that if you decrease the hole size, you should not get high energy gain, but this is something that happens. So again, we did numerical simulations to verify our predictions. So indeed we see that, so this red line shows the energy gain for a exponential or a non-ergodic accelerator, and this green line shows the energy gain for a quadratic or an ergodic accelerator as a function of 1 by h. So as 1 by h increases or the hole size decreases, the energy gain of my exponential accelerator actually increases, but the energy gain of my quadratic accelerator remains constant. So I showed you only 2 models, but we have studied this for few more models to see that the results are actually much more robust and not limited to the particular choice of examples which we have taken. So in summary, what we have found is that leaky non-ergodic billiards are much more efficient heaters, and this is not very obvious because you may think that if you have an exponential accelerator, the particles will accelerate very fast, and so it may also exit sooner, and hence the energy gain may remain roughly the same. But what we find that the answer is no, that actually non-ergodicity actually helps you in hitting the particle much faster. But it's important to note that this result is valid only when the exponential rate is large enough. Because you may have some systems which have an exponential growth of energy, but the exponent itself is a very small quantity. In that case, you will not be able to differentiate between ergodic and a non-ergodic accelerator. So it's important to have an exponential accelerator where the exponent is actually large enough compared to some number. And as I mentioned, the most important point is that heat production can be increased by decreasing the hole size. So this is the main sort of result of this paper. And if you're interested in more details, you can look at this. Paper. So if you have any questions, I'll be happy to answer.
Yeah, so when you say heat production, it is heat production per entry.
Yes, per entry, yes.
So, when you decrease the hole size, the frequency of entry decreases. No, it's a trivial point, but it's important to resolve the...
No, so here I have measured this E out minus E in times H. So my energy gain definition takes into account the amount of particles which are coming in.
I see.
So even though lesser particles are coming in, but the net effect is still so much larger that still you have higher energy gain even you have lesser number of particles coming in. That is why it is so much nice. Because if you actually just write E out minus E in, then the factor over here is 1 by h square. So when you multiply by h, still a 1 by h remains.
Okay.
And that gives you very high energy gain.
So I wanted to ask you about the second point of your conclusion.
Yes,
you said that exponential rate has to be large enough. Now, even suppose the rate is not so large, even in the long time limit, you cannot distinguish between.
Because what happens is that if you have a leaky system, then the particles may exit the billiard before the exponential rate starts showing its effect. Because if you write e power gamma t, you write it as 1 plus gamma t plus gamma square t square by 2 plus so on and so forth. So it has to stay inside my billiard for long enough time for the higher order terms to actually have an effect. So for example, I did this simulation for this trapezium also. So we know that this trapezium has exponential growth, but this trapezium and this stadium actually gave me the same energy gain. Because the exponential rate in this is so small that it takes a very long time for it to actually show an effect.
How large you need, that would depend on your hole size.
That will depend on my hole size, yes. So that is something that we have not studied very thoroughly, but maybe in the future we can. Yeah, so all our predictions are for an ensemble of non-interacting particles.
Yeah, so what happens when you have actual interacting particles like a plasma or something that you...
Yeah, so that is something that we have not studied very well, but the idea is that, so now let's say if you have a case of interacting particles in this system. So we believe, again, we are not very sure whether that will actually hold, but what we believe is that because this system is robust to all kinds of deformations, so basically you can model your interaction between your particles as perhaps some kind of potential in this region. Perhaps, I'm not very sure. But so because this system is robust to all those kinds of deformations, we hope that it will remain. But yeah, that needs to be studied in the future. So I'm trying to convince people to actually take it up and help me in doing those simulations. So maybe if you're interested, we can talk about it. Any other questions? Okay, thank you so much.
Let us thank the speaker again, and I'll invite the next speaker.